Section 8.1, Similarity in right triangles. These are the objectives. Use geometric mean to find segment lengths in right triangles. Second one, apply similarity relationships in right triangles to solve problems. Vocabulary, there it is. Next slide. This is the first term that you're going to be using in this section. Term 8.1.1. Follow along. It says the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. So in other words, there's all this is saying is when you have this situation, you have three triangles that are similar. I want you to pay attention to the size of the three triangles. The large triangle, medium size, and the small triangle. All three are similar. Let's move on to the next slide and apply this term. Here's number one. It says write a similarity statement comparing the three triangles. So this is what we're going to do. We're going to sketch the three triangles the following way. Notice that I have the large, the medium, and the small triangle. Why did I sketch them this way? Because of this. Notice that the corresponding sides match. Let me get right. Hypotenuse, hypotenuse, hypotenuse. Short leg, short leg, short leg. Long leg, long leg, long leg. Once you do this, once you sketch the three triangles the following way, it becomes a very easy problem, and this is the similarity statement that they're asking for. Let's move on to number two. It says write a similarity statement comparing the two triangles. I'm going to ask you to pause this for a second, and then I'm going to show you the answer in just a little bit and test yourself. So now, this is the answer. And once you sketch the two triangles just like number one, you're able to see that this is the similarity statement that we have as the answer. Let's move on to the next slide. This is definition. Follow along. It says the geometric mean of two positive numbers is the positive square root of their product. The geometric mean of a and b is a positive number x such that x squared is equal to a times b, or x is equal to the square root of the product ab. Let me give you an illustration of what the geometric mean represents. So let's say that we need to find the geometric mean of 4 and 9. Look at this rectangle. Look at it as a rectangle. This width is 4. This dimension is 4. This length is 9. Now notice that this is what I'm going to do. I'm going to find the geometric mean of 4 and 9, which turns out to be 6. Now let's go back to the rectangle and this new figure here, this new polygon. And if you look carefully, you know that this, actually we can call it a quadrilateral. Notice that this quadrilateral has the same area as this rectangle. So that's what basically what the geometric mean is representing geometrically. The area of this is 36. And the area of this is also 36. Okay? Let's move on to the next slide. I can clarify this in class if you like. Just ask. Let's move on to the next slide. It says find the geometric mean of each pair of numbers. If necessary, give the answer in simplest radical form. So let's do this. Let's let x be the geometric mean. And if I apply the formula or the definition that you saw on the previous slide, this is what I have. I have x squared is equal to 4 times 25, but I just want x not x squared, so then I take the square root of both sides, and I end up with x is equal to, or actually I just take the square root of the right hand side, and then I have x equals 10. Let's move on to number 4. Sometimes there are not all perfect squares, so in this case, we'll let x equal the geometric mean. So then I have to take the product of 5 and 30. And notice, since I'm going to have to take the square root of this side, I'm not going to multiply 5 times 30. I'm just going to break this up as 5 times 6. Why? Because I can very easily see that this is a perfect square, and that's why the answer is 5 radical 6. Let's move on to the next slide. Okay, let me read these two corollaries. These could be to a degree confusing, but follow along the examples, and again, ask for clarification if you need it in class. It says the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the two segments of the hypotenuse. So basically, this is talking about this is your height, this is your altitude, and it's equal to this. The altitude squared is equal to the product of this times this. Let's go to the other one. 813 says the length of a leg of a right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to the leg. This one is a little more confusing, but let's go to the picture. So let's focus on this one. So this squared, and that's what we have here, is equal to, notice that this side is adjacent to A, so it's x times the hypotenuse. Let's look at the other leg of this right triangle. So this leg here, this leg squared, b squared. Notice that this leg is adjacent to this side here, so b squared is equal to y times the hypotenuse, and that's what they have here. Let's move on to the next slide and apply these corollaries. Follow along. It says find u, v, and w. So let's bring the picture from the previous slide. So first we're going to find u. To find u, we're going to use corollary 812. And from the previous slide, this is what it said. H squared is equal to x times y. So this is your h. This is your h in the formula, in the problem. This is your h, like I said. And then the formula says x times y. So in the problem here, problem number 5, all you need to do is multiply u times 3. Once you apply corollary 812 into this problem, number 5, the height times this segment times this segment. And this is the equation that you're going to be working with. Now at this point, excuse me, all you're going to do is, this gives you 81, divide both sides by 3, and you end up with u is equal to 27. And this is the answer to u. Let's find v. So now that we know that u is 27, I know that this entire side, or what we call the hypotenuse of the large triangle, is 30. So let's find v. So to find v, now notice that this is a leg. To find the leg, I'm going to be using corollary 813. From the formula, it says a squared is equal to the side adjacent to it times the hypotenuse. And this is what we have. So I substitute the values from the problem that correspond to the formula. So I'm looking for v. So then I have v squared equals the side adjacent to it, which is 3, times the hypotenuse, which is 30. This is why I have this expression. At this point, I can multiply these two. It's not too bad. It's 90, and then I take the square root, and I end up with 3 radical 10. Why? Because 90 is the same thing as 9 times 10. Let's find w. So now to find w, notice that this is also a leg in the large right triangle. So I'm still using corollary 813. Corollary 813 in the from the previous slide. It says b squared is equal to y times c, which is this leg times the leg adjacent to it times the hypotenuse. So then, this is what I get. I have w squared, that's what you see here, times the leg that is adjacent to W, which is U, which is 30, times the, the other way around. Pause for a second. W squared, which is your leg, times the distance from here to here is not 30, it's actually 27, but I have it here, times the entire hypotenuse, which is 30, which is there. So 27 times 30 is the same thing as 30 times 27. And then at this point, all I need to do is, I can actually multiply these two numbers, but I'm not going to. I broke them up the following way. Why? Because I noticed that this is a perfect square, and this is also a perfect square. That's why I have, from here, if you break it up, you can go from here to here. You can skip this part. This is 9 radical 10, the answer to W. Let's move on to the last problem in this video. So word problem says, what is the height of the tree to the nearest meter? So we're going to let X represent the height above the eye level. And look at the picture. You know what the eye level is. So this is going to be my X from here all the way to here. So from here, this is the equation that I can generate. And basically, the formula that I'm using is corollary 812, which is this distance squared is equal to 1.6 times this distance, which is your X. And then at this point, you can just break out the calculator. You end up with this, divide both sides by 1.6, once we square this, and you end up with the following, approximate, you get 38. Then, is this the height of the tree, 38? The answer is no, because notice that you still have 1.6. So either this or this, either one works. This concludes the video.